Okay. So, Austin just came back from a hackathon at MIT,
How was that?
and you said it was awesome, but you didn't think the MIT people were as impressive as you expected. You were just as good.
Something like that, yeah.
Yeah.
I don't know. We all had our different specialties. Like our the first 7 hours of the hackathon or 8 hours of the hackathon was researching and prepping for. The original idea for the project was to do Google Maps indoors, but with visual keys. So like walk down the hall with your phone, and you'd be able to see like arrows on the floor,
Okay.
and then
So we do some kind of computer vision with machine learning for determining what was a left arrow versus a forward-facing arrow, something like that.
something like that, and then we also had a list of like tasks or APIs we had used or something could use to get we didn't have to, but we could use it. If we used it, then we were allowed to compete for another prize. So it was kind of
I got you. There was like an API specific prize type thing. Okay.
So there was a speech to text one that we were going to use for because obviously that's a very visual thing. So being able to make it applicable to people that aren't able to see. So speak where you'd like to go. That it responds with a response. We had gotten like pretty decently far in that. We had like building plans of MIT. We were mapping everything out geographically, and then we got to the point where I was like, okay, this is going to take us way too long to finish.
Okay.
So we want to meet up at some point and finish that project, but we ended up switching to an Android app.
Okay, so mid hackathon, you pivoted from indoor GPS to Android app for what?
Mainly time, but also.
No, like what did the Android app do?
Oh, sorry.
Yeah, what did you guys get?
We were using Amadeus, I think it's a travel API.
Okay.
So pulling in data from there to essentially Trivago, but you'd be able to explore your room in AR. So use Google Waypoint or Google, what are they called?
Well, explore what? Like your dorm room? What room are we talking about?
Like the idea would be that if this were implemented, then we'd have hotels that would send us, or we'd make 3D models of someone's room, and essentially you'd stand here, and you'd be able to walk into the room.
Gotcha. So augmented reality / VRE type thing for exploring a hotel room.
Yeah.
All right. So you pivoted from computer vision indoor mapping of the MIT campus to an Android app for looking at hotel rooms.
We were all disappointed, I know.
Interesting.
We wanted to do the first one, but time and then another factor, which I can explain later, but I don't really want to say it in public. So.
But in general, were the people on your team, were these people from MIT? Were they from a bunch of other universities? Who were the...
There was one from University of Texas, one from North Carolina University, and then one from India.
One from I got a university in India?
He's from the IIT, which is...
Okay, yeah, I know. That's basically the MIT of India.
Yeah.
Yep.
But saying it the nicest I can, he was definitely not as smart as he should have been.
Well, and that's kind of the point, right?
Yeah.
Is that just because you go to a school with a certain reputation or a certain name or something like that, you're going to have the same idiots everywhere, and you're going to have the same smart people everywhere. The best students we have here would fit in just fine at MIT, and the crappy students from here would fail out of MIT just like they would any place else. So it's but it was a good experience.
It was good, yeah. Honestly, if we could, I'd like to try and use some of their formatting for our 24-hour hackathon.
Sure. Yeah, we can sit down with me later and we can talk about what all they did and that stuff, because I'm definitely interested in that. Okay, so reminder, tonight is the next Tech Talk, right? Hosted by Jack, who's promised what we do, lobster tails, peel-and-eat shrimp. I think he's doing a fish fry. buffalo wings. All about it, yeah. Made to order steaks. He's bringing in Bobby Flay.
Glad I didn't miss
Okay,
it.
but what about buffalo lobster?
Buffalo lobster.
Yeah,
Okay.
exactly.
So I'm guessing maybe like cookies and stuff. But in any case, the speaker tonight is, I mentioned it the other day. He's the director of emerging technologies from Tesh Global. So it should be pretty interesting talking about kind of forward-thinking stuff. Format will be a little bit different, I think. It sounds like he has a slide set he sent us, so I'm guessing he's gonna kind of give a presentation, and I don't know if he's gonna kind of engage the audience and ask questions during it or open it up for questions at the end. I guess we'll just see. But that's kind of what it'll be. It's tonight at 6 p.m. until, let's call it 8 p.m. But I think we'll probably try to get started with the talk. The original idea would be that there would be like some networking time at the beginning, but that didn't really work out last time. So I think we'll probably just get rolling with the talk around 6:10-ish, something like that. After we confirm that the live link over to Ann Arbor is good. I'm guessing he'll talk until 7:15. Then we'll open up for questions, and then we'll be done. So that is tonight, and you are all cordially required to attend. So, and I gave the pitch for CU launch on Monday, correct? All right, good. Okay, so any questions before we dive in? Homework assignment, easy? But was I right that it was frustratingly easy?
Yep. Till
you wrapped your mind around what they were actually asking you to do? All right, so I told you to think about this in terms of some constructors, and if you were looking on Slack, I gave you a hint to maybe look ahead a little bit and kind of see how they were using those things to construct trees. Okay, so here is a tree that starts off as an interior node whose label is red, whose left child, or what is it, Elson, is an interior node whose label is bar, whose left son is a leaf of 26, whose right son, or arson, is a leaf of 12. This other guy's arson is an interior node with a label of red, whose Elson is a leaf of 11, whose arson is an interior node with a unpronounceable label, whose Elson is a leaf of 117, and whose arson is a leaf of 14. Constructors for building trees. Make sense? All right, so we're going to be using these constructors to do really hard stuff with trees, which is going to be fun for your next assignment. We might solve some of that. That's when we get into some of these 3. I think there's a 6-star one in here. It's actually done in invisible ink. So, it's a choose your own adventure question. All right, so what was the following procedures? Was this it? 131? Yeah, so we need a leaf in an interior node constructor, right? Okay. Francisco, you're late. You didn't bring me coffee.
Never asked.
I did.
Would you send a Slack message?
No, I asked in class.
Oh,
And I think, aren't we supposed to be responsible for anything that happens in class? V already got a 0 for the day for refusing to get the. Yeah, it was bad.
I don't even say no. I just don't answer your question.
It's like the same thing. All right, so we're going to define something called, was it interior node? Is that what it's called?
Yep.
An interior node is going to be a lambda. So this guy constructs an interior node. He's going to be a lambda that's going to take a symbol. He's going to take a Elson and an arson. Right? This is a symbol. Elson is a binary tree. Arson is a binary tree. And what is this guy going to return? He is going to return a list containing symbol, Elson, arson. That's it. That's what that guy does. He constructs an interior node. Give him 3 pieces of information. He will spit back to you a list containing those things. All right. This is our constructor. These are the attributes stored in list format for an interior node. Then we have define leaf to be a lambda. This guy takes a number as a parameter. And what does he do? He returns the number. Exhilarating stuff.
I felt like I was doing it wrong.
Now, does it all start coming into context now? And like I said this at the end of last class, right? That this question is like deceptively easy. And try to think about it in terms of constructors. All right, so that's leaf. This guy builds an interior node. This guy builds a leaf. If we look at the definition for a binary tree is either a number or it's a list containing a symbol, an elson, and an arson. Elson, arson, whatever, however we pronounce it. I'm using the old German. Okay. I don't even, whatever that means. All right, so now we're supposed to build a predicate called leaf that returns true if the dude we're looking at is a leaf and returns false otherwise. All right, and he's going to take a binary tree as a parameter. So we're going to define leaf question mark to be a lambda that's going to take a binary tree as a parameter, and we return true if this guy is a leaf node and false otherwise. So boil down to number bin tree. Number on bin tree will return true if bin tree was a number, and will return false otherwise. And since he's taking a binary tree as a parameter, his 2 options are either a leaf or a list. So a number or a list containing 3 things. Right? All right, so that's what leaf does. Let's see. Then we're supposed to write a elson, arson, and contents of. And these guys extract pieces of information from a interior node, effectively, right? So we'll do define. What was the contents of? Was what it was. Contents of. This guy will be a lambda that takes a bin tree. Now, we could assume it takes in a legal bin tree where contents of is a thing. So we'll boil down to the car of bin tree. Return the first element of that list. Define elson to be a lambda that takes in a bin tree, and he's going to return the car of the cooter of bin tree, the left son. Define arson to be a lambda that takes a bin tree, and he's going to return the car of the cooter of bin tree, which will be the 3rd element of the list. Make sense? Anything else? All right, that's the homework. This will make sense to everybody now. Deceptively simple. These are constructors that we can call that builds for us an organized tree. If I need a leaf, I can build a leaf. If I need an interior node, I can build an interior node. If I want to extract the left child, I can extract the left child, so on and so forth. All right. So questions about that? All right, so let's look at the next thing where we start doing stuff with this. So we're supposed to write a procedure called DoubleTree that takes a binary tree as represented in 1.17 and produces another binary tree that's like that one, but with all the integers and the leaves doubled. Okay, now what I'm going to do here is I'm going to steal this tree from down here just to give myself a tree to operate on. So I'm going to define test tree to be an interior node, blah, blah, blah. Okay, so that's the left son of that guy. That is the right son, and that's our test tree. All right, so test tree is an interior node with this symbol. Left son is an interior node with 2 child leaves. Right son is an interior node with this symbol. Left child is a leaf. Right child is an interior node. Left and right child are both leaves. So that is a tree built in terms of our constructors. So I should be able to call, like, for instance, leaf on test tree, and it should give me false. This dude is not a number. Oh, that's my little, we gotta fix the copy paste thingies. All right, so there's my false. Now, if I say, give me the contents of test tree, this guy should give me the symbol associated with that test tree, which is red. What do I call it?
You're missing an S.
Contents of. Nailed it. There's my red. If I ask for the LSON of test tree, it's going to give me the left child of this guy, which is this tree right here. And if I ask for the LSON of the LSON of test tree, test tree, it's going to give me the left son of the left son. Make sense? Okay. So I have a test tree that allows me to do some stuff. So now we're supposed to write a function here called DoubleTree. And this guy's going to take in a binary tree and he's going to produce a new tree. And that new tree is going to be just like the old tree, except all leaves are doubled. Right? What was it called? DoubleTree? Not the name of a hotel? It is the name of a hotel. Was that in your app? That's pretty funny, actually. DoubleTree is a Hilton hotel. So if you use Hilton API, you would have had DoubleTrees in there. All right, so define DoubleTree to be a lambda. That's going to take a bin tree as a parameter. And this guy's going to go through this bin tree, and he's going to produce a new bin tree that is just like the old bin tree, except whenever he sees a leaf, he's going to create a new leaf. And that new leaf is going to be a leaf whose value is twice as much as it used to be. Make sense? So we can ask the question, if leaf bin tree If I'm looking at a leaf, what do I do with it? I create a leaf that is binTree, well, that is times binTree 2.
That is stupidly easy.
That's my output.
That is stupid.
Boy, these constructors are handy.
A little bit.
Okay, so, if I'm looking at a leaf, double it, build a new leaf. Else, if I'm not looking at a leaf, what must I be looking at? Got to be looking at the other kind of binary tree, which is an interior node. Okay, and if it's an interior node, what do I need to do?
Make a new one.
I'm going to build a new interior node, and then I'm going to call DoubleTree on the left and the right side. So I will go ahead and I'll construct an interior node. Did I spell that right, Blaine? You're in charge of spelling.
Oh, I'm bad at spelling. I think so.
All right, I'm going to build an interior node. And interior nodes take 3 parameters. Contents of binTree is the first parameter. And then DoubleTree on the LSON of binTree and DoubleTree on the RSON of binTree.
Don't we want 2 times the contents of binTree?
No, this is a symbol. So, what are you expecting if you take 2 times that?
That is a fair question.
Yeah, we only do the double if it's a leaf. So if it's a leaf, what do? Well, we have no more recursion, right? That's the end of the road. If it's a leaf, it's just the number. What do? Build a new leaf that's twice that number. If it's not a leaf, here's the else. Must be an interior node. What do? We build a new interior node with the same contents as it used to be. Contents of extracts the contents for us. And calling DoubleTree on the left and the right side, because both of those guys are binTrees. And that's what DoubleTree does. It takes a binTree and performs the DoubleTree logic on it. Okay, so now I can call DoubleTree on, what is it, test tree? Is that right? Test tree. So that should be all of my leaves doubled. 5224, 5224, 22, 234, 28. Make sense?
Mm-hmm.
So these constructors pretty handy.
Well, that-
This predicate pretty handy. All right, so questions on DoubleTree. So we're manipulating binary trees here. Remember in 300 when we wrote binary trees? They weren't overly difficult, but there was a lot more to them than this, right? So binary trees are actually pretty simple. Now we're not doing it as a binary search tree, a BST tree, because that would require that the left and that the children are in certain orders, you know, for our constructor. But we could do that. We could write add functions to drop stuff into a tree and make sure they fall to the right place, building new trees each time. And we could do all that.
Why is the name of the next function so long?
Well, because it's awesome, obviously. In fact, we're going to copy that. That just has misspelling just written all over it. All right, next one. Write a procedure. This is a 2-star. Ooh, be rough. Write a procedure. Mark leaves with red depth. What does that even mean? That takes a binary tree. Okay, we've already been working with them, right? So it takes a binary tree and it produces a binary tree of the same shape as the original, except that in the new tree, each leaf contains the integer of nodes between it and the root that contains the symbol red. Okay. So let's see. Produces a binary, except that, and produces a binary tree of the same shape. Okay, so this is about the shape of this binary tree is an interior node with a left child and a right child. Here's the left child. The left child, this guy is a 1 depth away from the red. The right child is a 1 depth away from the red. This child is a 2 depth away from this red. This child is a 2 depth away from this red and a 2 depth away from this red. Well, it would have been better if they would have had one additional one, because if we had a left child here, wouldn't it have only been a 1 depth from this red?
I think it's counting the number of reds that have occurred before it.
Up to that point?
Yeah. Because otherwise...
So at this point, we've had 1 red, so both of these are 1. So leaves are just replaced with the number of reds.
Mhm.
And this one, we've had now a second red, so leaves are... Oh, okay, fine. So this guy is defined. Mark leaves with red depth to be a lambda that takes in a binary tree. We could do this with a let rec if we wanted to, or we can use a helper. So I'm actually going to call this guy helper. So let me come back to that here for in a second. So I'll define the normal one to be a lambda that takes in a bin tree, and he will call the helper, passing it the bin tree and an initial count of reds of 0. So this guy, this helper, is going to take in the binary tree it's operating on, as well as the number of reds so far. Okay, so we'll just ask the question, if leaf bin tree, and what's our output? Is it just the number? Yeah, it's just the number. If leaf bin tree, so if I'm looking at a leaf, rather than the number itself, we'll just return num reds. That's the number of reds we've run into at that point in time, presumably. Else, if I'm not looking at a leaf, I must be looking at an interior node. So I'm going to be interested in whether or not, in fact, we could write this as a cond if we want. That might make you happier. Instead of having an if instead of an if. So if leaf bin tree, then we'll return num reds. Else if the contents of bin tree EQ red, the contents of it is a red, then what are we going to do? We're going to, and does it leave the tree intact for that? Yes, it does. So we're going to build an interior node, and actually for, instead of just returning num reds here, which actually would give us the right answer, we're going to return the leaf version of num reds. So we're constructing a leaf. Output will end up being the same, but that's what we'll do if we see a leaf. Otherwise, if we're not looking at a leaf, we must be looking at an interior node. If the contents of that interior node is equal to red, then we're going to build an interior node, passing it contents of, that binary tree along with Mark leaves red blah blah helper this guy on the LSON of binTree along with plus num reds 1 and the Mark leaves with red blah blah with the RSON of binTree with plus num reds 1. So if we're looking at a label for a red, contents of is red, we're going to build an interior node with the same contents it currently has. So this would be red. We could just as easily hard code that to be red like that. But we'll go ahead and get the contents of, along with calling our helper on the left sun with a num reds greater 1 larger, because we found another red, and the R sun with a num reds 1 larger. Else, we must be looking at the interior node that does not have a contents of as a red. So we'll call the helper passing an LSON of binary tree along with num reds unchanged. I need to build an interior node of this. So we're going to build an interior node with contents of binTree along with the whatever helper returns on the LSON, not changing num reds, and whatever the helper returns on the RSON of binTree, not changing num reds. Like that. So now we should be able to call. Hey, what? Are you lying?
No, other Mark left down.
Oh, this guy. This dude.
No, that one. Yeah.
Liar? Yeah. There. So we'll call that dude on test tree. And it gives us our rest 1-1, blah, 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 blah. All right. Now, this is actually a good example of showing a reasonable use of let. So let me update this code a little bit to, because one of the things we should notice here is we're doing a lot of calling of the same stuff, aren't we?
Yeah.
For instance, LSON of binTree, LSON of binTree, contents of binTree, RSON of binTree. We're doing each of those at least twice. All right, so I'm going to take this code. We're just going to write it a second time using a let. So we'll call this guy helper 2. All right, and what we're going to do up here, in fact, I'm just going to steal this cont here real quick. All right, so we're going to build a let environment. We talked about lets last time, right? And we're going to define a couple of variables in here. So one of the variables, remember for a let, we have a list containing 2 lists, name value pairs. So in here, I'm going to have a contents, and that guy is going to be equal to contents. Actually, let's think about this. We got to do it this way. Before we do our let, we have to ask the question. So we're going to say if leaf binTree boil down to building a leaf with whatever numReds is. Okay? So if I'm looking at a leaf, build a leaf that has numReds in it. Else, we're going to create a let. And a let has a variable list followed by a body and a closing parenthesis. Okay? So for this variable list, we're going to have contents. Now we know that, we can even say contents of, we'll just keep it the same. So we know if I'm in this let that I'm dealing with a interior node. So contents of will equal contents of binTree. That's my first name value pair. Next name value pair, elson is equal to elson of binTree. That's my next name value pair. Arson is equal to arson of binTree. That's my next name value pair. That's the end of the things I need to remember. Now I'm going to do my, we can do an if we want, or we can do a con, but we'll just do an if. So we'll say if contents of, if that guy is equal to red, then what are we going to do? We're going to call, I'm going to just steal our helper 2 thing here. We're going to build an interior node. So interior node like that. We'll build an interior node with contents of elson, arson. But elson and arson we're going to pass to mark leaves helper elson. I'm going to kick it down the line here. And plus numReds1. Otherwise, helper arson plus numReds1. That's what we do if it's equal to red. Otherwise, we're going to build an interior node of contents of elson numReds and an interior node. Mark leaves with red depth helper 2, elson and numReds. So whatever that guy returns, so we're not changing numReds. And mark leaves helper 2, arson numReds. So this allowed us to create a let environment that had 3 variables so that we didn't have to resolve our binary tree multiple times. We stored in a variable called contents of, whatever the contents of our binary tree was. We stored an elson, whatever the elson of our binary tree was. We stored an arson, whatever the arson of our binary tree was. That then allowed us to ask questions. Is the contents of variable equal to red? If it is, build an interior node out of that contents of variable along with whatever's returned by our helper 2 for our elson variable and 1 greater than numReds, as well as helper 2 for our arson variable. Notice this is a variable. We're not having to call a function to extract stuff. So there aren't cars and cooters going on multiple times here. It's just that one variable that holds the already extracted right sun. Now, if it wasn't a red, then we do this other one where we just pass in num reds without changing it. And then to test this, we'll just call helper 2 instead of the original helper. And we should get the same output. So there's our output. All right, questions on that one? All right. All right. Write a procedure called, well, I'm very intrigued it has 3 stars next to it.
So it should be super easy.
All right, so write a procedure called path that takes an integer n and a binary search tree. So this is a new animal. Huh, there's going to be plenty of those, isn't it? All right, binary search tree is either an empty list or it's a list containing an integer and 2 binary search trees. This correctly describes the structure of each node, but ignores an important fact about binary search trees. All keys in the left subtree are less than or equal to the key in the current node, and all keys in the right subtree are greater than the key. That's something we talked about earlier, right? That there's an order to binary search trees. Because of this additional constraint, not every syntactic derivation of binary search tree leads to a correct binary search tree. Okay, yeah, they're basically saying this grammar here dictates what a binary search tree is, but doesn't actually enforce the rules of binary search trees. This grammar says, that there's 2 productions that make up a binary search tree. It can be an empty list, or it can be a list containing 3 elements: an int, a binary search tree, and another binary search tree. All right, that's what a binary search tree is. Okay, and what are we at? 1.31. That should get us into the right ballpark. All right, so path, what does this guy do? It takes a binary search tree that contains the integer n and returns a list of lefts and rights showing how to find the node containing n. If n is found at the root, it returns the empty list. Okay, so this does, basically the book is saying we must follow the real rules of binary search tree, even though the grammar does not dictate it. So they're saying, hey, we're humans, we know what we're computer scientists, so we know what binary search trees are. Binary search trees have this underlying definition that any number, the stuff to the left of it is less than or equal to it, anything to the right of it is greater than it. That's the rules of binary search tree. The grammar syntax isn't smart enough to dictate that. So we have to just know that's the rule, so we can technically construct things that are grammatically correct by the binary search tree language without following the binary search tree rules. But for the purpose of this path function, they're saying, assume that they've created a binary search tree that does follow the rules. That is, your top level guy here is a 17. His left subtree has a 14 in it. That guy's right subtree has a 12 in it, which is smaller than a 14, but both of them are less than a 17. Okay, so it's following the binary search tree rules for this guy. That make sense? All right, so That's what path is going to do. And then what we are going to do is we're going to write a function that when you go in here, you're searching for a number. So for instance, we might search for, I guess just path was what we were searching for. So same thing I was saying before, just we have 14, its left tree is 7, 7 is less than or equal to 14. Its right tree is, his right tree is this is his whole left tree. His right tree is the 26, which is greater than 14. So it follows the rules. And then, so when we say 17, what we'll do is we'll give it the almost like GPS instructions. So kind of like, mapping the inside of MIT type thing. Except we'll make it work. We'll probably write this next time because I'm going to give you the next one as the assignment. I'll explain in a second. But what we'll do is when we look for a 17, it's going to tell us that, 17 will be to the right of 14. It'll be to the left of 26. And then it'll be to the left of the 20. That's the path to get there. So it tells you the GPS, the turns to take to traverse the tree to get to the right place. All right, so we'll write that. So remind me 1.34 for next class. For your homework, we're going to write 1.35. So this guy's still working with binary trees, not binary search trees. So this is write a procedure called number leaves that takes a bin tree, the thing we've been working with all class today. Okay, not this new binary search tree thing, but this bin tree, and produces a binary tree, a bin tree, that's like the original, except the contents of the leaves are numbered starting from 0. So for example, if we have number of leaves past this tree, this guy should boil down to foo bar. It's really surprising that they still use that in examples in books. Well, I'm not going to say it on recording. So this guy takes in foo bar. This is leaf 0. This is leaf 1. This is leaf 2. This is leaf 3. This is leaf 4. It numbers the leaves. So whenever we run into something that is a leaf, we have to say which leaf was this guy. That make sense? Okay. Now, where does this get difficult? It gets difficult in that when you have 2 trees, we're going to make potentially 2 recursive calls, right? Well, we don't know how many leaves we're going to find. So you notice here for this guy, this has a left node of 26 and a right node of 12. Now, this left tree could have had several things in it, right? But this particular case, it only had one thing in it. So this guy boiled down to 0. If this left subtree had more things in it, would his children have been 1 and 2? Or would it have been at the top level? We can see the answer to that with the second part here. So we have an interior node here whose left tree was this 11 here, which is a 2. That's the next thing we ran into. Keep in mind that that is the left child of the first tree. This is the right child of that tree. Anything that happens on the left happens before the things that happen on the right. It's almost kind of like merge sort. We have to wait for the entire left side to be processed before we can process the right side, to have our accurate starting point for which leaf number are we dealing with for the right side. We couldn't deal with this right child until we knew that we were done with the left child and the last marked child was a 1. From that point forward, our starting point was 2. If this left side was super complex, we might have been starting with a 60 here, for all we know. You're going to find let stars, let recs may be somewhat beneficial here. Because you're going to need to process the left sun first in its entirety. Make sense? All right, questions, comments, concerns, bribes.
How much of a bribe?
Should be big bucks for this one. This is 3 stars. All right, so I'll see everybody at the Tech Talk tonight. I'll put this assignment up, and I will see you when I see you.
I'll give you a fresh pancake.